Example 7.2, using series and parallel reduction techniques, what are the power dissipated by resistors 2 ohm, 14 ohm, and delivered by the power supply? So we want to use resistor reduction to simplify the left side, that is left to the power supply, and the right side, which is to the right of the power supply, while keeping in mind a 14 and a 2 ohm resistor here. So in this situation, let's say that we're talking about this 14 ohm resistor. So we want to pay attention to this 14 ohm resistor. Note, it doesn't matter whether I say the one on the left or the right. And the other one that we want to pay attention to is this 2 ohm resistor. Now, what you're seeing here is that there's no value to the power supply, for voltage-wise, that is. There's only the current. So because we have no voltage value, or the power supply, only the current value at 13 amps, using the current divider rule, is the best option. So as before, we want to use the color coding. Okay. So if I look at the, maybe I should write this down, using coloring and node labeling, here's what I'm going to find. I have my circuit, and it looks like this. So this is just an image of the circuit. So this is the image of the circuit. So the bottom of the power supply, I'm always going to define as ground. There are some instances where that may not be useful, but for the vast majority of the time in this course, definitely yes. And I'm going to say that the top of the power supply, I'm going to label in red, and we know that that's the value of the source voltage, but we don't have that. But I'm going to call that node A. Then here I go. I'm going to call this guy node B. I'm going to call this one over here node C. And then down here, the ground, I'm going to call node D. So I want to rewrite this. So look at between A and B. I have two 14 ohm resistors in parallel. Look at between B and D. I have two 6 ohm resistors in parallel. And then if you look at between C and D, I have two resistors in parallel. So I have three reductions that we can use. So we want to do three reductions. So do three parallel reductions. And here we go. There's A and B has two 14 ohm resistors in parallel, which then tells us then that the resistance between A and B, remember what it is, it's the addition of the two resistors divided by the product of the two resistors. And when the dust settles, we get 7 ohms. Now look at the 6. So between B and D has a 6 ohm parallel to a 6 ohm. So if I now do the exact same thing, I'm going to have 6 plus 6 divided into 6 times 6. So this is going to give me a 3 ohm resistor. And then finally, I have between C and D has 6 parallel to 2. So then the resistance between C and D are then going to be 6 plus 2 divided by 6 times 2, which then gives me 1.5 ohms. So I now have 3 resistors instead of 6 resistors. Now let's redraw the circuit. So redraw the equivalent circuit. So then I'm seeing that the resistance A to B is going to go like this, right? That's A to B. And then I'm going to have another resistor, which is going to be the resistor between B and D. This is 7 ohms. This is 3 ohms. And then I have, of course, my power supply here. And then if I go to the other branch, I have one resistor that's already at 1.5. And then I have my equivalent resistor, which is RCD. And this is 1.5 ohms. And this is 1.5 ohms. So now I have the following. I don't know what the source voltage is, so I'm not even going to bother putting it in, but I do see that I have this current flowing in. And excuse me, flowing out. And this is 13 amps. So if I color code everything again, here we go. I have my red node, A. I have my green node, B. I have my blue node, C. And finally, I have my ground, which I labeled as D. So where are the powers that we want to calculate? In here, between C and D here, here's where the 2 ohm resistor lives. And then over here in the 7 ohm, here's where the 14 ohm lives. So that's what we're interested in. So to calculate these powers, to calculate the powers of the 14 ohm and 2 ohm, we can use one of 3 possible relations. We know that the power of a resistor is the voltage of the resistor times the current of the resistor. This would be inefficient because I need to calculate 2 things. The other thing that we can do is that we could use the voltage of the resistor. We can calculate that divided in by the resistance, or we could use the current of the resistor times its resistance values. Since we already have currents, it makes most sense to do this here. So here we should say that it makes sense to use this form since we only have a current source value. So in my mind, I am thinking CDR to calculate those currents. Now, the first thing that I would pay attention is that I want to grab this circuit right here. So I'm going to grab this and I'm going to copy this for later use. So the first thing that I would look at is that look at these two resistors. I have RAB in series with RBD. They have the same, they're in series, so they're going to have the same current. So when I look at this 1.5 and RCD, these are also in series and they have the same current. So it makes sense to use CDR to calculate the current. So that way I know the current through RAB. I know the current through RCD. So let's do that. So use CDR to calculate the currents through the left and right branches. So let's simplify the circuit. So note each branch has two resistors in series, implying they have the same currents. And that's going to be very useful. So I'm going to modify the circuit from what I have. And here's what we just did. So I'm going to modify this. So I'm going to take this away. I'm going to take that away. And I'm going to move it over here. And this is what I'm going to do. I know that these two resistors on the left are in series, so I could make them into one. These two resistors are in series, and I could make them into one. So now I'm going to simplify them. So if I simplify them, here's what I have. I have a resistor. And this is going to be the resistor AD. Whoa, I don't think I like that notation. I'm going to say ABD, and then I'm going to come and look at my source, and then I'm going to have a second resistor, and this is going to have a resistance of RACD, and it's going to look like this. And once again, I still have 13 amps going in that direction. So when I'm looking at this, let's look at this resistor. So resistor ABD has two resistors in series. So it's RAB plus RBD, and that's going to give us 7 plus 3 which will give us a 10 ohm. I think I want to move this over here a bit more. So with that being said, I know that this guy is a 10 ohm resistor. Now, if I look at resistor RCD, this is the same as the resistance between AC plus CD. So I get 1.5 plus 1.5. That's going to give me 3 ohms. So I know that this guy is 3 ohms. So now I see that that 13 amp is being split. So as it's being split, part of the current has to go in this direction, and part of the current has to go in that direction. So I'm going to label these as left and right. So I'm going to say that this is the current of the left branch, and then this is the current of the right branch. So these resistors are in parallel, and we should apply CDR to calculate those currents. So first, determine R parallel for this circuit. So I have R parallel. Maybe I should be more careful. How about if we do it, if I have R parallel over 1, that's going to equal to 1 over R A B D plus 1 over A C D. But if I do my manipulation, I have the algebraic identity that this will be RABD times RACD divided by the sum of these guys. So if I now put in my values, this will be 10 plus 3 divided into 10 times 3. And if I calculate that resistance, I get 2.31 ohms. So now I know what R parallel is. Now we can apply the current divider rule. Okay. Applying CDR, then here we go. The current of the left is equal to R parallel divided by R ABD times 13 amps. So this will then be 2.31 10 ohms times 13 amps, and I get a value of 3 amps, and that's the current to the left. So now I have that current. Then I repeat the process And then I get, so if you're seeing here, if I compare 10 to 3, you could see that it's 3 times. So this should be more than 3 times, like 3 1/3. So you could probably guess that numerically it has to be 10 amps. So now I have my currents. Now we can calculate the powers. To calculate the powers the 14 ohm and the 2 ohm, we start unfolding these equivalent resistances. So let's look at the left branch. So we're going to look at the left branch. And the power of the 14 ohm. So here's what we see. So if you look at the circuit here, I have a 10 ohm. That 10 ohm is a combination of a 7 and 3. But remember, the 7 contains the two 14s. So let's write that out. So if I follow my sequence of unfolding, I know that, how do I draw this nice and neat? I know that I have to have this guy. And I have a single resistor, and that's our equivalent. So this guy is our RABD. And when I look at this, this is a 10 ohm resistor. So I see that I have a current coming in that's 3 amps. But series elements have the same resistance. I mean, the same current. So when I look at this guy, this is now the same as a 7 ohm and a 3 ohm. So when I look at that current, this current coming down is still 3 amps, and it continues to be 3 amps going through the 3 ohm too. But we only care about the 7 one. So now if I look at the 7 one, I see that we have 2 resistors that are 14 ohm. So this is still 3 ohms, but now this is 14 ohms and this is 14 ohms. And I see here that I have this current coming in. And I have 3 amps like that. So now what's going to happen? These currents are going to get divided. So what does CDR say? So CDR tells us then that the current of the 14 ohm should be the current of R parallel divided by the 14 ohm. But look what we're seeing here. R parallel in this case is the 7 ohm. So then, oops, I forgot to do that. This is times 3 amps, so this should be 7 ohms, 14 ohms times 3 amps. So that's going to give me a current of 1.5 amps. So now that I have this current, I could now go in and actually calculate the power. So if I calculate the power, then we say that the power of the 14 ohm is the current of the 14 ohm squared times the resistance of the 14 ohm. So then this will then be 1.5 amps squared times 14 ohms. So I get a positive 31.5 watts, and that's the power of the 14 ohm. So now I'm just going to repeat the process here. Now we want to repeat the same process for the left branch to calculate the 2 ohm. So we're on the right branch. And the power of the 2 ohm. Now, this is a repeat of the previous section. So to try to save time, I'm going to copy this and then just modify it. So if I come in here and paste it, remember, this is an old calculation, but we want to modify it. So first thing I got to do is I got to get rid of the currents. Right? The CDR is going to be different. We're talking about a different resistor. And our load resistor is for ACD, which is a 3 ohm resistor. And what happens is that we have a current coming in, and this current is 3 times the size. So when we look at these resistors here, this is 1.5 ohms. This is 1.5 ohms. And so if I'm looking at the current coming in here also goes through here, and this guy's 10 amps. This is 10 amps. And so now we have to modify our circuit here. So the way I'll modify it is that we have this guy down here at the bottom. And we have this guy up here at the top. So more or less, this is our circuit right here. So what do we know? Well, we know this. We know that this guy is 1.5 ohms. This is a 3.3 ohm, and this is a 3 ohm. No, it's not. It's a 6 and a 2. This is a 6, and this is a 2. So now the same process happens. I'm looking at the circuit, and it says I still have 10 amps coming down here. But what's going to happen is that you're going to see that the current here is now going to split to the left and to the right. We are most interested in the 2 ohm resistor. So if I look at the current of the 2 ohm, it's going to then be, I have the R parallel. Now what's the R parallel? It's this guy is the R parallel. And then I have my 2 ohm and I have my resistor. So when I look at this guy, this then reads like this. I'm going to have 1.5 ohms times 2 ohms times 3. Nope, not 3. It's got to be 10 amps. And the bottom line is that now I'm going to get 3 halves. So it's 30 divided by 4, which should give me 7.5 amps. So now I know the current. This is my current. Now we could calculate what the power is. The power of the 2 ohm is, it's got to be its current times its resistance, current squared, of course. So then this will be 7.5 amps squared times 2 ohms, and that ends up being 113 watts to 3 sig figs. So now I know my power. So what's left here is calculating the power of the source current. So calculating the power supply power, which is the power of the 13 amp source. So if I look at this, we say that the power of the 13 amp source has to be its voltage times its current. We know the current, we don't know the voltage. So when I write this out, we see here is that we need to focus on this voltage. And from example 1, typically the information that you have available is what really, really helps to reduce what you have to calculate. We have the available information to compute the voltage of this 13 amp source. So I'm going to come up here and I need to get the circuit. So I'm going to say that this is the circuit that we want, because we made some calculations already. And this is what the calculations showed. We don't care about the currents, these currents, because we've already computed them. And what we know here is that in this branch, we had 3 amps, and in this branch, we had 10 amps. Just by using Ohm's law, we can clearly see that we know what the voltage is of one of the branches. And since this is V source, which is what we want to calculate, and this guy down here is the ground, we could then say that from Ohm's law, we could see that the voltage of the 13 amp source has to be the branch on the left, which also has to be the branch on the right, and they should give us the same values. So if you look at this thing, look at the left. The left is going to be 3 amps times 10 ohms, and on the right, it's going to be 10 amp times 3 ohms, and you can clearly see that that's a 30 volt value. So this right here is the voltage of that source. So now we could calculate the power delivered. The power delivered by the power supply is then going to be the power of the 13 amp source is going to be its voltage times its current, which then tells us that that has to be minus, because it's an active source, it's got to be 30 volts times 13 amps, and that has to be minus 390 watts. And that's the power of the 13 amp source. So now we've calculated all of the powers here. So something that you may have realized, let's check our power calculations. So what we assumed here is that the power delivered should be the power absorbed. So what was delivered? Well, we clearly see that this has to be 390, but what did we calculate? The question is, what did we calculate? Well, we calculated the power of the 14 ohm plus the power of the 2 ohm, and if we start computing these values, one of them is 31.5 watts, the other one is 113 watts, and you could see here that they're not equal. Is that a surprise? This is expected, that they are not equal. We did not include all the terms. Now, if I go and I look at an image of the circuit, look what we're actually seeing here. So if I look at the actual circuit, well, look, if you're looking at the power absorbed, there's a lot more terms, right? There's 2 powers of the 14 ohm. There's 2 powers of the 6 ohm. There is the power of the 1.5 ohm, and of course, there's the power of the 6 ohm, and then there's the power of the 2 ohm. If we were to sum all of these, then we would get 390 watts. But that's not what we did.